first paper delivered as a pre-recorded session by Raziye Aghapour is on the topic Probabilistic Planning of Electric Vehicle Charging Stations in an Integrated Electric Transport System. Raziye received the MSc degree in Electrical Engineering, Management Control and Navigation of Power Systems from Shahid Beheshti University, Tehran, Iran. Her research interests lie in distribution systems operation and planning, electric vehicle demand response, and renewable energy integration. Before we start, I would like to let you know that questions can be posed via the Q&A function in your screen. Without further ado, we shall start playing her pre-recorded presentation.
Everyone, my name is Raziye Aghapour. I'm a graduate student from the Department of Electrical Engineering at Shahid Beheshti University in Iran. My supervisor, Mohammad, Sadegh, Sepasian, and our colleagues, Hamidreza, Arasteh from Neuro Research Institute, Vahid, Vahidinasab from Newcastle University, and João, Catalão from University of Porto, and Institute for System and Computer Engineering, Technology and Science have helped me to prepare this paper. Today, I'd like to make a presentation on the paper entitled Probabilistic Planning of Electric Vehicles Charging Station in an Integrated Electricity Transport System. This is the outline I will be going through as the presentation progresses. First of all, I'd like to explain why we need to allocate charging stations. Electric vehicles gain increasing importance in transportation due to their role in reducing the production of greenhouse gases. Limited all-electric range of these vehicles and needing urgent charging in long-distance travel would necessitate the development of electric vehicles charging infrastructures such as fast charging stations. But the uncontrolled nature of charging demand can lead to a stochastic charging load, which may have adverse effects on distribution system, such as losses and voltage drops. So, the optimal planning of fast charging stations is essential to achieve the benefits of electric vehicles. Here are several aspects contribute to our presentation. Firstly, electric vehicles move on traffic network roads, so any study related to EVs would be unrealistic without transportation features. So, we use user equilibrium-based traffic assignment method to model spatial and temporal distribution of electric vehicles. Secondly, we model the uncertain behavior of EV drivers as well as the load levels based on the queuing theory. Then we consider the minimizing of annual investment costs and energy losses of distribution power system as our objective function and model the problem under chance constraint optimization framework. Finally, in order to propagate the uncertainties to decision making, we introduced probability dominance criteria. You will encounter all of the topics as the presentation moves forward. This is the general outline of the problem formulation. We are going to minimize the annual investment cost as well as the annual cost of energy losses subject to capacity limit of charging station and power system operational constraint consisting line flow and voltage limits. As you can see on the left of the screen, the proposed model is divided into 5 main sections. 1. Traffic assignment. What does traffic assignment mean? Take, for example, 5 vehicles want to travel from the origin O to the destination D. We use the user equilibrium-based traffic assignment model to estimate the volume of traffic on the passes between the origin O and the destination D. By these results, we can calculate the number of vehicles passing through the traffic nodes. So, the average number of vehicles arriving in candidate node for building the fast charging station can be expressed in terms of traffic factors including C, the total number of charging of EVs, FFT, the trip ratio, and F, the number of vehicles passing through the traffic candidate nodes, and the response of EV drivers to charging tariffs term. We will come back to the effect of this term later. Capacity determination. EV's stochastic arrival in and leaving from charging stations are modeled using a queuing system. In the MMS queuing model, S stands for the number of identical charging devices. The first M denotes the arrival of vehicles in charging station, which is based on the Poisson process with the parameter lambda, which we just discussed about it. And the second M is the service time for each charging devices. Here, EV drivers are considered as customers who need to refuel, and if all charging devices are busy, they will have to wait in a queue. In this system, service quality is largely determined by an average waiting time for refueling. So this enables us to optimize the capacity of charging station in terms of the patience of EV drivers. According to the queuing theory, the average waiting time for charging service can be calculated. If the waiting time of a customer is over a permissible period, they will leave. In other words, the constraint waiting time less than permissible waiting time is used to determine the capacity of the charging stations. Charging load formation. The setting of charging stations would reflect the charging demand. The charging demand of the charging station can be expressed as the number of charging devices at service, which can be obtained based on the queuing model, multiplied by the charging rate of the charging devices. You can find the detailed formulation in the paper. As I mentioned before, this stochastic load may have an adverse effect on the distribution power system. This leads us to analyze the impact of this added load on voltages and line flows of the distribution system. So, the planning of charging stations needs to take care of the uncertain load of the distribution system. In this way, we use the chance constraint to make sure constraints are satisfied with the predefined confidence interval alpha. In order to find the confidence interval of voltages and line flows, a probabilistic power flow would be solved to obtain the PDFs of voltages and line flows. We use the point estimation method and Grand-Charlier expansion to approximate the probabilistic distribution functions. Let's look at our objective function again. As you can see, the term annual cost of energy losses is probabilistic, so our objective function is probabilistic too. Consider two generic alternatives A and B. The mean value of B is larger than that of A, but the variance of A, which is commonly used measure of risk, is smaller than that of B. So, if decision maker wants to select one of these solutions, a comparison between two PDFs should be performed. To this aim, we use three probability dominance criteria: mean variance method, stochastic dominance method, probabilistic exceedance measure. The risk of the plan, in addition to its mean value, is investigated by this comparison method. When a list of non-dominant plans is formed, a decision maker can choose one non-dominant plan based on its interests, such as closeness to shopping centers. Now, I'd like to move on to the results part. This figure shows the graphical topology of the coupled distribution and transportation system. The Sioux Falls traffic network and the corresponding 33 bus distribution test system are used here. As shown in the figure, common nodes between the traffic and distribution system are considered as a candidate location for the construction of fast charging stations. The described model is investigated on this network, and the results are analyzed via three scenarios. First, the mean values of charging demands and conventional loads are considered as input data, and the problem is modeled as deterministic optimization. The investment cost of this case is $635,245. The location of the charging station as well as the number of charging devices at each are summarized in the table. Then we use the chance constraint programming to model the uncertainty of the problem. The set of feasible plans are shown in this table. To show the accuracy of the probabilistic approach, we compare our method with Monte Carlo simulation. In this graph, the combined point estimation method and Graham-Charlier expansion technique, which is denoted by PEMGSE in the graph, is used to obtain the cumulative distribution function of a bus voltage. The cumulative distribution function is compared with that obtained using the Monte Carlo simulation. As you can see, our model provides a good fitting to the cumulative distribution function obtained with the Monte Carlo method. So, the proposed model can significantly reduce the computational time while maintaining a high degree of accuracy. Now let's take a look at comparison with the deterministic model. Results shows that the optimum plan of the deterministic scenario is not feasible according to the second scenario. Moreover, the planning cost increased when we consider the uncertainties. This shows the importance of considering the uncertainties. Now I'd like to draw your attention to the left column of the table. The variance term implies the risk of the alternative plans. In this way, the probability dominance criteria is used for comparing the objective function of the feasible plans. So, the decision maker can confidently choose from non-dominant plans based on its priorities. As highlighted in the table, the third and fifth plans are non-dominant in terms of the mean cost and risk. As I mentioned on earlier sections, we considered the effect of different electricity tariffs on arrival rate of EVs in charging stations. Here we have interesting results. According to these tables, both the mean and variance of the cost of the feasible plans in this case are lower than those without considering the electricity tariffs. This proves the performance and effectiveness of a proper electricity tariff design. Here, the second and fourth plans are non-dominant. The selection of the final solution is not focused in this paper. Here are the key points of our presentation. As innovation parts of our work, we assess most probabilistic aspects of the problem in a reasonable amount of time and with a sufficient degree of certainty, and analyze the effect of different electricity tariffs on the behavior of EV drivers. The results show that the presence of uncertainties may significantly change the planning decisions, and by applying the proper electricity tariffs, not only the investment risk could be decreased, but also the planning of charging station could be managed in a more economical way. As our future works, we want to use a proper method for solving the proposed model in larger scale case studies and consider the effect of different charging tariffs on drivers' route choice behavior and its implication on traffic assignment. Last but not least, we acknowledge the support by FEDER and by Portuguese funds. This brings me to the end of my presentation. Thank you for your attention.
Excellent timing and a very well delivered presentation in your video. There is a question for you in the Q&A, and the question is,
Yeah.
how did you account for electricity tariffs?
Well, as can I put my background on? May I put my background on?
Yes.
Okay.
Any other?
Well, do you see my background?
No,
Okay, I answered. Well, as I mentioned in the presentation, the average number of EVs arriving at charging station formulates in terms of traffic factors and response of EV drivers to electricity tariffs. So we consider both peak hours of power distribution network and rush hours of traffic network to design the times and the prices of electricity
tariffs. Jordan Holwer, would that answer your question?
Thank you. I hope
Excellent.
this
Excellent.
answer
Very well done.
was clear now. Thank you.
Very good. We have time for another question. Has anybody else have a question for? Well, I do have a simple question for you, Raziye, and is how is your methodology only applicable to city-based traffic distribution systems, or it's also applicable to countrywide, motorways, or freeways systems?
Well, our traffic assignment model generally used in urban traffic design, so we can and power distribution system constraint and formulation is not specific, so we can apply this model on large scale case studies.
Okay, thank you very much. Yes, I do understand. Thank you very much. Any other quick question from the floor?
I have a quick question. As a presenter, I don't think I can put it in the Q&A, but great presentation. My question was, do you allow vehicles to be delayed if that reduces the cost, or do you assume that they will always charge if a charger is available?
No, actually, we consider waiting time as a limit to determine our fast charging station size. Well, according to our model, if waiting time of a customer longer than a permissible waiting time, they will leave.
Would that answer your question?
Yes, I think so.
Oh, excellent. Thank you very much. Well, perhaps it would be time to move on to the next presentation. Thank you very much, Raziye, for a very good presentation.
Thank you.
Well, on that point, perhaps I would like to move on to the presentation.